But have you ever stopped to think about the power held by charges that aren't moving? Just present.
Yeah, it's a different perspective.
That's the world of electrostatics, and believe it or not, these seemingly still forces are behind some truly surprising and impactful phenomena.
Absolutely.
Today, we're taking a deep dive into a fascinating set of sources you shared, aiming to uncover the hidden world of electrostatics beyond, that annoying zap you get from a carpet.
And what's fascinating here is how utterly fundamental these concepts are. I mean, we're not just talking about static cling.
Right.
We're looking at the basic principles governing everything from how atoms bond together to massive industrial processes and even the delicate machinery of life itself.
Wow.
So our goal today is to sort of illuminate these connections and show you just how deeply electrostatics is woven into the fabric of our world.
Exactly. So our exploration today will kick off with the core rules that dictate how these charges interact, the ultimate give and take of attraction and repulsion. And then we'll journey through their surprisingly sophisticated applications in everything from cleaning the air we breathe to the very structure of our DNA. Ready to have your perspective positively charged?
Absolutely. Let's lay the groundwork. The absolute cornerstone of electrostatics has got to be Coulomb's law.
Coulomb's law, right?
This is the fundamental rule. It quantifies the force between any two charged particles.
Okay, so picture two tiny bits of charge just sort of hanging out. Coulomb's law tells us that the force between them, whether they're drawn together or pushed apart, hinges on two key things.
Exactly. The amount of charge each one possesses, and crucially the distance separating them.
Okay.
The law states that the force is directly linked to the product of the charges. So bigger charges mean stronger force. Makes sense.
Yeah.
But it's inversely proportional to the square of the distance between them.
Ah, the inverse square part.
Yeah. And this inverse square relationship is really significant if you, say, double the distance.
The force gets much weaker.
By a factor of 4, exactly. It drops off quickly.
And there's a neat little formula that captures this, isn't there? FKKRA.
That's the one.
Okay, let's break that down simply. F is the electrostatic force we're talking about.
Yep.
K is Coulomb's constant. Think of it as a fundamental number, right? Roughly 8.987510 arrow. Newton meters squared per Coulomb squared. It sort of sets the overall strength of this whole interaction.
Perfect description. It's the scaling factor. Then you've got q and q, which just represent the amount of charge on our two particles.
Okay.
And r is simply the distance between their centers.
Got it. That's a pretty accessible breakdown.
And the critical insight from this law, the thing we touched on, is that fundamental principle. Like charges repel, opposites attract.
The golden rule.
It is. This simple yet profound rule dictates interactions across all scales, from tiny subatomic particles right up to the macroscopic world.
And it's kind of amazing how this seemingly simple force is responsible for, holding all the matter around us together at the atomic level, isn't it?
Absolutely. That attraction between the positive nucleus and the negative electrons, that's Coulomb's law in action right there.
Okay, so we've got a handle on the forces, but these charges, they also create an invisible influence field around themselves.
That's the concept of the electric field, yeah.
Yeah.
Imagine it as the region of space surrounding a charged object where another charged object would feel a force.
Ah, okay.
Now, closely linked to this is the electrostatic potential, which we often just call voltage.
Voltage, right, like electrical pressure.
So it's a great way to think about it. Voltage is like the electrical pressure or even potential energy per unit charge at a given point in that field.
So the electric field is the actual push or pull a charge would feel. And the voltage is like the electrical height. A charge at a higher voltage has the potential to fall towards a lower voltage, doing work maybe?
That's a really good, relatable analogy. And mathematically, they're tightly linked. The electric field's strength and direction are directly related to how quickly the voltage changes over distance.
Okay.
Think of it like this. The electric field lines always point downhill in terms of voltage, from areas of higher potential to lower potential.
Like contour lines on a map showing steepness.
Exactly like that. And these mathematical tools, the field and potential, allow scientists to precisely map out and predict how things will behave for really any configuration of charges you can imagine.
Fascinating. It's like having a topographical map of the electrical landscape.
Oh.
Okay, now let's delve into some of the cool things these static charges can actually do. We've all felt that little shock, but there's way more to it, isn't there?
Oh, absolutely. Let's start with something called electrostatic induction.
Induction, okay.
Imagine you bring a charged object, say positive, near a neutral piece of metal, but don't touch it. What happens inside the metal?
Well, metals have electrons that can move around easily, right?
Exactly, they're conductors.
So if you bring a positive charge close, the negative electrons in the metal would be drawn towards that side, while the positive atomic cores, which are fixed, effectively make the other side more positive because the electrons have left. So the charge is separate.
Precisely. Even though the metal as a whole is still neutral, the charges inside redistribute. That separation of charge within a neutral conductor, just triggered by a nearby charge, that's electrostatic induction.
No actual contact needed.
Nope. It's influence at a distance,
Yeah.
a really fundamental way charges interact.
Okay, cool. And then we have static electricity itself, that familiar zap. What's the basic science there?
At its heart, static electricity is simply an imbalance of electric charges built up on the surface of a material.
An excess or a deficit of electrons, usually.
Right. And this imbalance just sits there, it persists, until those excess charges find a path to move away and neutralize, usually through an electric current or, more suddenly, an electrical discharge.
Like the zap.
Like the zap. Think about rubbing a balloon on your hair. You're physically scraping electrons off one surface onto the other, creating that imbalance.
Yeah, so that's why your hair might stand on end. Each strand gets the same charge and repels the others.
Yep.
Or why the balloon sticks to the wall. It induces an opposite charge in the wall surface through that induction thing we just talked about.
You got it. And that sudden spark when you touch a metal doorknob after walking on carpet,
Yeah.
especially on a dry day,
Yeah.
that's the electrostatic discharge. The built-up charge on you finds a quick path through you to the doorknob to ground, neutralizing itself. Ouch.
Okay, and you mentioned rubbing things together. There's a specific name for that effect, right?
Yes, the triboelectric effect.
Triboelectric. Sounds technical. What's the gist?
It's actually pretty straightforward. It's just the separation of charges that happens when two different materials come into contact and are then separated.
Just contact, or does rubbing help?
Rubbing definitely helps because it increases the contact area and the energy involved. But even just touching and separating different materials can transfer some electrons,
Why different materials?
because different materials have different affinities for electrons. One material might hold onto its electrons more tightly than the other. So when they touch, electrons tend to jump from the one with lower affinity to the one with higher affinity.
Leaving one positive and the other negative.
Exactly. That's the most common way everyday static electricity gets generated. The balloon in hair is a classic example.
Right. Okay, so we've gone from forces to fields to induction and those everyday zaps. Now let's get to the really fascinating part. How we've cleverly harnessed these static charges for some amazing applications. I was genuinely surprised that the first industrial use was way back in 1907.
Yeah, it might seem a bit old school, but electrostatics has been a real workhorse in industry for over a century. One of the earliest and still hugely important applications is electrostatic precipitation.
Precipitation, like rain. How does that work for pollution?
Not quite like rain. It's used for air pollution control, mainly removing particles from industrial exhaust gases, like from power plants or factories.
Okay, so static electricity cleans the air. How?
Essentially, you give the tiny pollutant particles in the gas, stream, dust, soot, whatever, an electrostatic charge, usually negative.
You charge up the pollution.
Yep. Then these charged particles are passed through an electric field created between, say, high voltage wires and grounded collecting plates.
Ah, so the field pulls them.
Exactly. The electric field exerts a force on the charged particles, making them migrate towards the oppositely charged collecting plates and stick there.
Like a magnet pulling iron filings?
Sort of, but with electric fields and charges. Then, periodically, you remove the collected gunk from the plates. The result is remarkably cleaner air coming out the smokestack.
How effective is it?
It's incredibly effective. Efficiencies often reach 90 to 99%, even for really fine aerosol particles, especially in humid gases.
Wow, 99%. So this isn't just some niche thing. It's having a massive impact on air quality.
A huge impact. Think about the emissions from coal-fired power plants. Electrostatic precipitators are crucial there.
That's genuinely impressive. What other industrial tricks use electrostatics?
Electrostatic coating is another big one, especially for painting.
Painting. How does static help paint stick?
Well, a common method uses high-speed rotary atomizers. They spin really fast to create a very fine mist of paint droplets.
Okay, tiny droplets.
Then you give these droplets an electrostatic charge as they leave the atomizer. The object you want to paint is usually grounded, or sometimes given the opposite charge.
So the charged paint is attracted to the object.
Strongly attracted.
Okay.
Instead of just spraying paint in the general direction and hoping enough lands where you want it.
Which wastes a lot of paint and creates overspray.
Right. The charged particles are drawn directly to the grounded object. They even wrap around corners to some extent because the electric field lines bend.
Oh, neat.
This means a much more uniform coat, significantly less overspray pollution, and much higher transfer efficiency. More paint ends up on the object, less is wasted.
That's smart. Lower pollution, less waste, better finish. Win-win-win.
Exactly. And powder coating works on a very similar principle. You spray charged, dry powder particles onto the object.
And they stick electrostatically.
They stick, and then you usually bake the object to melt and fuse the powder into a smooth, durable coating. It's used a lot for things like appliances and car parts.
Ingenious. Using that fundamental attraction so effectively. Okay, let's switch gears to technology. Photocopiers, everyone knows they use static, but the details are kind of a black box for most people, including me.
Sure. The process is called xerography dry writing, basically. It's really clever. The heart of it is a drum coated with a special material, often selenium.
Selenium. Why selenium?
Because it's a photoconductor. That means it acts as an electrical insulator when it's in the dark.
Okay.
But it becomes conductive when light shines on it, like a light-activated switch for electricity flow.
Interesting property. So how does that make a copy?
First, you give the entire surface of this drum a uniform positive charge in the dark.
Okay, drum's charged.
Then, you project an image of the document you want to copy onto the drum using a bright light and lenses.
Ah, so light hits the drum where the original paper was white.
Exactly. And where the light hits, the selenium becomes conductive.
And the charge flows away.
Right. The positive charge in the illuminated areas leaks away through the now conductive selenium to the grounded drum beneath, neutralizing those areas. But the areas corresponding to the dark parts of the image, the text or pictures, remain dark on the drum.
So they stay insulating.
And they keep their positive charge. So now you have an invisible electrostatic pattern, a latent image, on the drum surface made of charge.
Wow, okay. An electrical ghost image. What's next?
Next, you cascade very fine black powder particles called toner over the drum. This toner is specially formulated to pick up a negative charge.
Negatively charged toner.
Ah, I see where this is going.
The negatively charged toner particles are attracted to.
The positively charged areas left on the drum, the latent image.
Precisely. The toner sticks only to the parts of the drum that didn't get hit by light. So now the image is visible in toner on the drum. How does it get onto the paper?
Finally, you bring a sheet of paper into contact with the drum. Before it touches, the paper is given an even stronger positive charge than the drum's latent image had.
Stronger positive charge.
Yeah. So the negatively charged toner particles are now more strongly attracted to the paper than they are to the drum. They transfer over.
And make the image on the paper.
Exactly. Then the paper goes through heated rollers, which melt the toner particles and fuse them permanently onto the paper fibers. And out comes your copy.
That is such an intricate, elegant dance of physics.
Yeah.
Amazing. What about inkjet printers? Tiny droplets, I know, but where's the static?
Many common inkjet printers use electrostatics to steer the ink droplets. As the tiny droplets are shot out of the printhead nozzles,
Yeah.
they pass between pairs of charged deflector plates.
Like tiny parallel plates creating an electric field.
Exactly. By precisely controlling the voltage, and therefore the electric field strength, between these plates, the printer can deflect the path of each individual charged ink droplet.
So you can steer them left or right, up or down.
With incredible precision. This allows the printer to direct each microscopic drop to exactly the right spot on the paper to build up text and images. It's like an electrical guidance system.
That's remarkably sophisticated control. I also read something about NASA using electrostatics for dust removal. Sounds critical for space missions.
Oh, very critical. Dust is a huge problem in space, whether it's lunar dust, Martian dust, or just contaminants on sensitive equipment.
Gritty stuff.
Very. NASA's Electrostatics and Surface Physics Lab works on this. They're developing technologies using electrostatic fields to actively repel dust particles from surfaces, like solar panels or astronaut visors.
Using repulsion instead of attraction.
Right. Or to attract dust onto designated collection surfaces to clean the air inside spacecraft or habitats. It's a really active area of research.
Makes total sense, using the force to keep things clean. And then there are these super tiny devices, MEMS and NEMS, micro and nano electromechanical systems. Electrostatics is big there too.
Absolutely crucial. At these incredibly small scales, the electrostatic pull-in phenomenon becomes really important and useful.
Pull in.
Yeah. Imagine you have two tiny conductive components separated by a microscopic gap. If you apply voltage across that gap, you create an electrostatic attractive force between them.
Like tiny capacitor plates wanting to touch.
Exactly. And because the components are so small and light and the gap is so tiny, that electrostatic force can actually become strong enough to physically pull one component towards the other until they make contact.
So it acts like an electrically triggered switch. Or a tiny muscle.
Precisely. It's used to make microscopic relays and switches. It's also the principle behind many MEMS sensors, like accelerometers in your phone, that detect motion movement, changes the gap, which changes the capacitance or triggers a pull-in event.
Wow, so these electrostatic forces, which seem weak at our scale, become dominant and really useful when things get tiny.
They really do. The scaling works in their favor at the micro and nano levels.
Okay, we've seen industry and tech. But perhaps the most mind-blowing part is how fundamental electrostatics is to, well, life itself, biology. I was fascinated by its role in DNA. Static electricity helps hold our genes together.
It's absolutely critical. DNA is a highly, highly charged molecule. Its backbone is made of phosphate groups, each carrying a negative charge.
So it's like a long string of negative charges.
A very long string, about 2 fundamental units of negative charge every 0.3 nanometers or so. That's incredibly dense.
Wouldn't all that negative charge want to fly apart? Repulsion?
It absolutely would. That inherent repulsion is a major force shaping the molecule. But it's carefully balanced.
Balanced by what?
By a few things. Positively charged ions, like magnesium or sodium, floating around in the cell nucleus cluster around the DNA, shielding those negative charges from each other. That's electrostatic screening. We can talk more about that. Also, specific positively charged proteins called histones wrap the DNA around them, neutralizing the charge. And then, crucially, there are the hydrogen bonds between the DNA bases holding the two strands of the double helix together. These bonds, while often described chemically, are fundamentally electrostatic attractions between partially positive hydrogen atoms and partially negative oxygen or nitrogen atoms.
So it's this complex interplay repulsion, pushing it apart, attraction and shielding, holding it together, that gives DNA its specific, stable double helix shape.
Exactly. Electrostatics is absolutely key to DNA structure, stability, and how it interacts with other molecules.
Amazing. And then there's the cell membrane. It has an electrical potential across it, like a tiny battery.
That's a perfect analogy. The transmembrane electrostatic potential is a major energy source for the cell. There's a voltage difference across the membrane, typically with the inside being negative relative to the outside, maybe 70 millivolts or so in a nerve cell at rest.
Minus 70 millivolts, okay. What does that voltage do?
It does a huge amount. It drives the transport of ions and other molecules across the membrane through specialized protein channels and pumps. It influences the shape and function of countless membrane proteins that have charged parts. It's essential for cell signaling, energy production. It's a fundamental aspect of cell life.
Like a built-in power source and control system.
Pretty much, yeah. A dynamic one, too.
And I also gathered that electrostatic forces are vital for proteins, too, how they fold up and do their jobs.
Oh, absolutely. Proteins are made of amino acids, and many of those amino acids have side chains that are either fully charged, positive or negative, or polar, having partial positive and negative ends.
So proteins are studded with charges.
They are, and these charges interact. Positive side chains are attracted to negative ones, forming salt bridges or ion pairs. Polar groups form hydrogen bonds. Even repulsion between charges helps dictate the shape.
And the shape is everything for a protein's function, right?
Everything. These electrostatic interactions are crucial forces that guide the protein chain to fold into its specific, complex, three-dimensional structure. That precise shape creates pockets for binding other molecules or surfaces for catalyzing reactions.
So if you mess with the charges, you mess with the function.
Definitely.
Yeah.
And cells actually do this deliberately. Adding or removing charged groups, like phosphate groups in a process called phosphorylation, is a major way cells switch proteins on or off. It changes the electrostatic interactions within the protein, alters its shape, and thus controls its activity.
Wow, so charge modulation is a control mechanism.
A key one. Changes in pH, which affect protonation states, also heavily influence protein electrostatics and function.
And finally, in this biological tour, nerve impulses. That's electrical, obviously, but it's about ions moving across that membrane potential we talked about.
Exactly. A nerve impulse, or action potential, is essentially a rapid, temporary change in that transmembrane potential. It relies entirely on the controlled movement of charged ions, mainly sodium, Ni, and potassium, Cop, across the nerve cell membrane, Through voltage-gated ion channels. Voltage-gated. They open and close based on the voltage. Precisely. A stimulus causes some channels to open, ions flow in or out, changing the local voltage. This voltage change triggers nearby voltage-gated channels to open, propagating the change along the nerve fiber like a wave.
Driven by both the concentration differences of the ions
and the electrical potential difference across the membrane. It's an electrochemical process, deeply rooted in electrostatics.
It's mind-boggling to think these same basic static forces govern photocopiers and our thoughts. Okay, stepping back a bit, what's the cutting edge look like? What's happening in modern electrostatics research?
Well, there are several really active frontiers. On the theoretical side, advanced computer modeling is giving us much deeper insights. For instance, understanding electrostatic self-assembly.
How charged things spontaneously arrange themselves.
Yeah, like nanoparticles forming ordered structures. Models are showing, for example, that you often need a certain minimum amount of charge on the surface of these particles.
Why is that?
To overcome the tendency of the solvent, usually water in biological or chemical systems, to kind of get in the way and screen the charges from each other, you need enough oomph to push the solvent molecules aside and let the attraction take over.
So the environment matters hugely. And speaking of tiny things, what about applying this at the nanoscale? Building things.
Electrostatic deposition using electric fields to place nanoscale components is proving very effective. But again, the solvent plays a really complex role.
How so?
Depending on the specific nanoparticles, the surface they're landing on, and the solvent itself, the solvent can either help the assembly along or completely hinder it. Understanding and controlling those solvent effects is a big challenge for making new nanomaterials reliably.
Right, and we talked about biological membranes earlier. What's new there?
We're learning more about how different membranes within the same cell have distinct electrical personalities, you could say.
Different charges.
Yeah, different surface charge densities. This is mainly due to the specific mix of phospholipid molecules making up that particular membrane. For instance, the plasma membrane, the outer boundary, tends to be the most negatively charged on its inner face. Then maybe the Golgi, lysosomes, ER membranes have slightly different charges.
Why does that matter?
It likely affects which proteins associate with which membrane, how vesicles butt off and fuse, all sorts of trafficking and signaling events. Researchers are also really digging into the electromechanical behavior now.
Electromechanical. How charge affects the physical properties.
Exactly. How the surface charges and the transmembrane potential influence the membrane stiffness, its curvature, its ability to bend and deform. This is super important for processes like cell division, vesicle formation, and even how nerve signals propagate mechanically along the axon.
So the electrical state affects the physical state.
Very much so. It's a tightly coupled system.
That's fascinating. Now, thinking about these biological systems, are there unique factors compared to, say, charges in a vacuum or air? You mentioned screening.
Yeah, electrostatic screening is huge in biology. The inside of a cell is crowded with water molecules, ions, proteins, all sorts of charged and polar stuff.
A real soup?
And a very complex electrical soup. This means the force between any two specific charges is significantly weakened or screened compared to what it would be in a vacuum. The other charges and the polar water molecules arrange themselves to partially counteract the electric field.
So Coulomb's law still applies fundamentally, but the effective force you feel is much less over distance.
Precisely. The reach of the electrostatic interaction is much shorter in that salty, watery environment.
Okay, that makes sense. And what about dielectric properties? You mentioned the membrane acting as a barrier.
Right. The dielectric constant is a measure of how well a material can reduce an electric field passing through it, essentially by polarizing itself.
Water has a high dielectric constant, right? It's good at screening.
Very high, around 80. But the inside of a cell membrane, the lipid part, is very nonpolar. It has a very low dielectric constant, maybe 2 or 3.
Big difference.
Huge difference. This creates what's called a dielectric barrier. It's energetically very unfavorable for a charged ion to move from the high dielectric water into the low dielectric membrane interior.
Ah, so that's why ions don't just leak across the membrane easily?
That's a major reason, yes. It contributes significantly to the membrane's impermeability to ions, forcing them to use specific protein channels or transporters to get across. It's an electrical insulation layer, in effect.
So the membrane is both a physical and an electrical barrier.
Definitely. The ability of materials to polarize their electric polarizability or permittivity is key to all these effects.
Okay. Looking ahead then, what's the future hold? Where might we see electrostatics making new waves?
The potential is really broad. We can expect more sophisticated industrial uses, better MEMS and NEMS devices.
Tinier sensors and actuators.
Right. Innovations in biotechnology, maybe using electrostatics for more targeted drug delivery or new diagnostic tools. Also, handling ultrafine particles for creating advanced materials with novel properties.
And space tech.
And space tech, yeah.
Hmm.
Better dust mitigation is one thing, but people even talk about exotic ideas like electrostatic propulsion, though that's more speculative.
Intriguing. What specific research areas are paving the way for this?
Well, people are working hard on understanding and controlling electrostatic friction, or stiction, which is a big issue in tiny devices and maybe future displays.
Preventing things from sticking together unexpectedly.
Exactly. Also preventing dielectric breakdown insulation failure in things like electric motors or high voltage equipment to make them more reliable and efficient, and developing better ways to measure those dielectric properties of materials, especially for things like designing microwave circuits or waveguides for communications.
And I assume the biological side is still humming with activity?
Oh, absolutely. A huge goal right now is to develop better tools to actually see and measure these electrostatic properties, membrane potential, surface charge in living cells in real time with high resolution during dynamic processes.
Like watching the charges change as a cell engulfs something.
Exactly. Watching the electrostatics during phagocytosis or during cell signaling events. Current methods are often indirect or average over large areas or times. We need more dynamic, localized techniques to really understand how these forces orchestrate life's processes moment by moment.
Wow. It really is incredible when you step back and consider the sheer scope of electrostatics, from, the way atoms stick together to cleaning factory smoke, making copies, and literally powering our cells and nerves. It's
Yeah.
so much more than static cling.
It truly is. These fundamental principles we've been discussing, they aren't just abstract physics concepts. They're actively shaping the technology we use constantly, and they're absolutely fundamental to understanding life itself.
So here's a final thought for you listening. We usually only notice electrostatics in that brief, maybe annoying static shock. But considering everything we've touched on today, industry, technology, the very core of biology, isn't it amazing to think about how this fundamental force, often invisible, is constantly silently at work, orchestrating so many different things all around us and even inside us? It really makes you wonder what other unseen forces are shaping our world, doesn't it?